for your intellectual stimulation, an increase in development of your knowledge of chemistry, you can expect to see bonus quiz 2 this afternoon. Posted, of course, to Sakai. Now, last time, we discussed the possibility of changing the solubility of a salt of limited solubility in water by providing the metal ion component of the salt the opportunity to react with a Lewis base, given that the metal ion component of the salt can behave as a Lewis acid. And by this Lewis acid-Lewis base reaction, convert the salt to a complex ion. A complex ion containing the metal ion of the original salt. Like dissolving silver chloride by treatment with ammonia, which results in producing the silver ammonia complex ion as the metal ion containing complex ion. After we did this, which we did in this cylinder, I asked the question, chloride ion, ammonia, water. The 3 Lewis bases in this system. Which wins the battle in competition for silver ion? Or to put it another way, which of these Lewis bases seems to form the stronger bonds to silver ion? If my memory is right, across the board you voted for ammonia. Because in what we did, we dissolved the silver chloride rather readily by treatment with 6 molar ammonia solution. The equation for this reaction, written as an equilibrium, is this. K is calculated by recognizing as this reaction talks to us. KSP for this stuff multiplied times KF for this stuff. The equilibrium constant, which corresponds to the formation of this stuff by reaction of silver ion AQ with ammonia molecules AQ. KF for the silver ammonia complex ion, we wrote on the board last time, it's in the notes, is 1.7 times 10 to the 7th. That's a big number. Tells you that this stuff is pretty doggone stable. But when we do this calculation, which corresponds to the conversion of silver chloride by treatment with ammonia to the silver ammonia complex ion, we get a value of 0.0029. What's this tell you? What's this tell you about bond strength competition? Chloride ion versus ammonia, and their relative abilities to make bonds with silver ion. What's this result tell you? Or what's this result suggest? Sound like ammonia wins? Not entirely. Well, be careful of the word entirely, because these are all equilibrium systems. Entirely means 100%, or the converse of which is 0%. Well, let's analyze this system further. Let's imagine that we wish to compute the solubility of silver chloride in 6.0 molar ammonia, given that we dissolved the silver chloride in 6.0 molar ammonia. Now, one of the questions I'd like to ask you regarding this equilibrium system is, does this equilibrium system live in this cylinder? Is that equilibrium system alive and well in this system, in this cylinder? Yes or no? Sounds like the jury is hung. How many vote yes? No looking around, just me. How many vote no? The no's are right. Why are the no's, and I don't mean K-N-O-W-S, why are the no votes correct?
Because there has to be precipitate with the
Silver chloride. See any silver chloride in here? No. So the system we created involved a complete dissolving of silver chloride. Which means, if nothing else, by way of the gang-up factor, we supplied enough ammonia in the system to get all the silver chloride to dissolve. Now I could add some more chloride ion to this system, and I'm sure get some of the silver chloride to reappear, which would at that point mean we'd have this equilibrium. But that's not necessary in order to get at determination of which is the stronger bond former to silver ion. Is it ammonia or chloride ion? So on with the calculation. Let's imagine that I dissolve some but not all of the silver chloride. Or if you wish, as I just said, we could add more chloride ion to this system and get the silver chloride, at least some of it, to reappear. If S represents the solubility of silver chloride in 6.0 molar ammonia, and the system which we are considering involved treatment of pure silver chloride with ammonia solution. Now we don't even have that system, because what we did was to mix sodium chloride solution, 1.0 molar, with silver ion solution, specifically silver nitrate solution, 0.02 molar. So would you like to bet there's some chloride ion floating around in here? Since we mixed 0.02 molar silver ion with 1 molar chloride ion. Good bet there's chloride ion floating around in there. But we did the dissolving by treating with 6 molar ammonia. So the mole ratio of ammonia to chloride ion for the systems we use, for the solutions we use to make this system, was 6:1. So the gang-up factor is certainly in favor of ammonia, which, as you'll see in a moment, relates to why we succeeded in dissolving the silver chloride so readily. Back to the analysis. If the system is prepared by treating silver chloride with ammonia solution, we can then represent the solubility of silver chloride as being equal to the silver ammonia complex ion concentration as well as the chloride ion concentration. In this system, the chloride ion concentration will not simply be S. It will also be related to the molarity of chloride ion, which we built into the system by preparing the system using sodium chloride solution. Well, at this point, we want to simplify the calculation so that we can be sure to understand the chemistry. Then you can make the numbers more complicated. If you understand the chemistry, the numbers part is easy. If you don't understand the chemistry, then nothing else matters. All right? So if these molarities are equal, we got S squared up top, and the ammonia molarity at equilibrium will be the initial molarity of 6.0 less, 2S. Because this tells us, per mole of this dissolved, you have to consume 2 moles of ammonia. Glad I noticed that. So we do the arithmetic. How do we proceed with the arithmetic? Well, if you treat this as it stands, it's a quadratic. You know me, I don't fool around with quadratics. But there is an arithmetic method or arithmetic approach which we can follow to turn this into a very simple statement. What is this arithmetic approach? You see this is a perfect square? And this is just a number. The square root of this number is bigger or smaller than this number? Bigger than this number. But we take the square root, turn it into a first order expression, where this now becomes S over the quantity 6.0 minus 2S. Solve it, we get 0.29 molar. So take note, if 1.0 moles silver chloride is treated with 1.0 liters of 6.0 molar ammonia. This number tells us that in this system, at equilibrium, how many moles of this do we have? How many moles? 0.29 moles. Just did the arithmetic. And remember, molar concentration and moles total are equivalent values when system volume is 1 liter. So, how much silver chloride is still there if we made this system? Thus, moles AgCl undissolved. How many? How much? Nothing fancy about this. .71 moles of silver chloride still there. So look at this system quantitatively. Or, in addition to the quantitative considerations we've already made. Mole of this, which means that we got 1 mole silver ion total, 1 mole chloride ion total. We'll gang up on chloride ion 6 to 1, because in 1 liter of 6.0 molar ammonia, we got 6 moles of ammonia. Stoichiometrically, this statement tells us, per mole of silver chloride dissolved by this reaction, you need 2 moles of ammonia. We got 6 moles of ammonia per mole of silver chloride. Yet, ganging up on chloride ion with ammonia by a factor of 6 to 1, after equilibrium is established, only 0.29 moles of silver ammonia complex ion formed, while 0.71 moles of silver chloride have remained intact and undissolved. Who makes the stronger bonds with silver ion? Chloride ion does. How about that? See, I purposely misled you when I made this system. Or I really didn't purposely mislead you, but I didn't talk about the details, which we just have, by reminding you, as I just did, but not when we made the system, that you cannot directly decide who makes the stronger bonds toward silver ion. Is it chloride ion or ammonia? When we made a system where the amount of moles of ammonia in the system far exceeds the amount of moles of chloride ion. That's misleading. That's like going back to the fighting ring when the whole bunch of us, plus the whole Gator football team, jumps on Muhammad Ali. Just because we eventually do him in, after 60 or 80 of us probably get killed along the way, that's hardly proof that we're stronger. See how the game plays? Good. Now then, before we proceed, I want to take another look at this system. I've written this up here. Silver chloride dissolved by ammonia, that's what we did. What happens on treating this with 6 molar nitric acid solution? I've got the 6 molar nitric acid solution right here. Here's the system we created last time. Silver chloride dissolved by treatment with ammonia. I'm going to treat this with 6 molar nitric acid solution, but before we apply this treatment, I'm asking you to tell me what is going to happen. What will we see? I'm listening. Will we see the reformation of silver chloride? Because when I take this system, even though we really don't have the equilibrium, we already talked about that, but in this system we got this and this, and extra this floating around. When I take this system and whack it with hydronium ion, because that's what I do when I add the 6 molar nitric acid solution, what am I going to murder? Am I going to murder this? Do I expect to murder this? Why not? Ammonia is readily attackable by hydronium ion. So if this murdering takes place as you have predicted, we should see the redevelopment of silver chloride. Now then, you will see this. What I want you to pay attention to, though, as I now proceed to add the 6 molar nitric acid solution to our system, is not just the reprecipitation of silver chloride, but what you see above the liquid part of the system, which is down here. I want you to pay attention to what you see up here, okay? Oops. What do you see up there? What is this? I defy you to see ammonia. It's a transparent material, as are all real gases, unless they're colored. What is this stuff? Would you accept if I call this stuff a smoke? Does it look like a smoke? Good. Back to Chemistry 2045. What is a smoke? What is a smoke? I'm not asking how it's produced. I'm asking what is a smoke? You see a smoke. Define smoke. And I don't mean cigarette. Particles in air. These particles to which you refer. Are they vapor phase, liquid phase, or solid phase? Solid. That's correct. So smoke is a heterogeneous mixture of a solid in a vapor, commonly air. So what is this smoke? Specifically, what is this smoke? Because you've recognized that this smoke has been created by the formation of a solid in the vapor phase part of this system, the system that's above the liquid part. You see all the silver chloride came back. We're talking about the smoke. What is the smoke? What's the solid component of this smoke?
Silver chloride?
No.
Silver nitrate?
Silver nitrate. No. How do you think you will proceed with this analysis to find out the nature of the smoke? What will you do? What we do? Yes! Pay attention to what the hell's in the system. PSI. All right? Now, to give you some support in recognizing how to treat this PSI, I'm going to draw a $64,000 sketch on the board, which simulates work that you did in 46 Laboratory during assignment number 2. Wouldn't you pay $64,000 for that?
Yes.
Bunsen burner, flame, crucible, not suspended in air, but resting on a clay triangle. I don't want to draw all that part. You remember doing this in assignment 2? Specifically in assignment 2, 46L. Do you remember taking some ammonium chloride, placing a small quantity of ammonium chloride in the crucible, heating it strongly? What did you observe when you did that? You see smoke?
Yes.
What was the smoke? What was the smoke? You did this in lab. What the hell was the smoke? Are you in lab doing things you don't even know what's going on? What was the smoke? What was the smoke?
NH4 plus.
No. I can't get a bottle of ions all by itself. If I could, then I'll go get my bottle of electrons and repeat the experiment which I described to you before of going home and sticking the electrons in my electrical system at home and watching the television televate and all that stuff and telling GRU to go to hell, which we cannot do.
The smoke was basic, so it had to have ammonia in it.
Wrong. There's what you put in the crucible. You heat it strongly. You saw this smoke up here. We told you to keep on heating until the observance of smoke was no longer made. The smoke was not produced anymore. And after you did that and let the crucible cool off, you look back at the crucible, no ammonium chloride remaining. What's the smoke? Ammonium chloride, you're damn right. What chemistry did you do by heating this stuff strongly? What chemistry took place when you heated this stuff strongly?
Sublimation.
What?
Sublimation.
No.
Combustion.
No. You didn't see a flame come out of the crucible, did you?
Vaporization.
What?
Vaporization. Vaporization?
No. You did this in lab. It's explained in the discussion for assignment 2 in the laboratory manual. Did you read that stuff? I'm going to go back and be a lab TA. And I'm going to hover over every damn lab section. And you're not getting a damned okay, not a 1, until you demonstrate understanding of what the heck's there. Because your job is to learn, and without understanding, you don't learn. You've heard me say this before, haven't you? You think you hear me say it again? Maybe 1,000 more times? Or more? When you heated this stuff strongly, you created an acid-base reaction. How about that? By strong heating, with no solvent being present, you force the transfer of H plus from the weak acid ammonium ion to the very weak base chloride ion, producing 2 volatile products, HCl gas and ammonia gas. These gases came out of the crucible because their kinetic energies are quite high as a consequence of this strong heating. But as they leave the crucible and rise higher in air, they cool off. And they meet each other. In fact, it's a mixture of ammonia and HCl leaving the crucible. But when they cool off, they have the opportunity to do what? Re-react. And when they re-react, bingo! And that's your smoke. What was this smoke?
HCl.
No!
HCl.
Ammonium what?
HCl.
No! It's a solid. It's a gas. What's the smoke that we saw here? Inventory. PSI. What did we put together? Ammonium nitrate. You're damn right. Look at what happened. We had an atmosphere up here rich in ammonia because we treated this with an excess ammonia. Okay? So in this atmosphere, you couldn't see it, but it's there. Ammonia. I remind you again, gases are transparent. You can't see gases unless they happen to be colored. Okay? So through this atmosphere rich in ammonia, you've poured hydronium ion and nitrate ion. The hydronium ion hit these ammonia molecules and did what to them? Turned them into ammonium ions. And the ammonium ions looked around and said, anything minus in this atmosphere? Said, but these nitrate ions coming along. Beep! Ammonium nitrate. There's your smoke. Difficult, yes. But if you pay attention to the PSI for the system, you can figure out what's going on. Fun, isn't it? I've been doing this with classes for I don't know how long. I've not yet found anybody who's been able to tell me what the smoke is first go round. Even though I stand here and jump up and down. Pay attention to PSI. What did we do? See? The same old story. If you do not know what is in a chemical system, you cannot possibly understand the chemistry that will occur or does occur in the system. And this is where general chemistry textbooks fall apart totally because they do not do this at all. All they have you do is follow recipes. Here's a problem. And what's the hell's the problem at the end of the chapter? Same problem, different numbers. Take the numbers, jam them into what you see, and you get an answer. Oh, I accomplished something. You accomplished nothing except learning how to be a mimic. That's why those rotten, worthless books do not get into this classroom. Not as long as I got blood flowing in my veins. Because they stand in the way of learning. And we're here to learn. Not to learn how to be mimics. You've heard this sermon before. You'll hear it again. We proceed. Let's take a look at another material of limited solubility in water, specifically silver oxide. Right now, I want you to recognize that if I take silver oxide and hit it with ammonia, it will dissolve much more readily than silver chloride. And if you do the analysis like we did here, you'll find out that oxide ion and ammonia have about the same bond-forming strengths with silver ion. When you dissolve silver oxide with ammonia, here's the silver-containing product. Okay? When you dissolve silver oxide with the ammonium ion ammonia buffer, there's the silver-containing product. But when you dissolve silver oxide with ammonium nitrate solution, this is not the only silver-containing product. Yet, for these three systems, you get three different reaction equations. It's your responsibility to write these reaction equations. But I want you purposely to tackle this one, because this one is the most challenging. Right now, on your paper, let's go. I'm telling you this. Silver oxide is treated with ammonium ion in aqueous media. One of the silver-containing products is the silver ammonia complex ion. You complete the reaction equation. Do it now. Let's go. This is what I gave you. Finish it. Finish it now. To write this equation correctly, you will have to pay attention to, carefully pay attention to stoichiometry. Would you like some assistance? When ammonium ion interacts with oxide ion, or a source of oxide ion like silver oxide, what do we get?
Hydroxide in the room.
When ammonium ion interacts with oxide ion, with the ammonium ion being in excess. When ammonium ion interacts with oxide ion, with the ammonium ion being in excess, what do we get as products?
Hydroxide.
Water. Yeah, you get water, right?
Don't you dare tell me hydroxide ion. I'm not making something which will also react with ammonium ion. You get water and?
Ammonia.
Water and ammonia. That's right. Now then, for this reaction equation, ammonium ion plus oxide ion, to make water and ammonia. Per mole of oxide ion, how many moles of ammonium ion are required? So by this chemistry, 2 moles of ammonium ion clobbering 1 mole of oxide ion and a mole of silver oxide. How many moles of ammonia are produced? How many moles of ammonia are produced? 2. How many moles of silver ion can I complex with 2 moles of ammonia? 1. How many moles of silver ion in a mole of silver oxide? 2. What's the other silver containing product? What is it? That's it. Simply silver ion. That's it. And water. But we talked about the other silver containing thing. As I said, I purposely picked on this one because it's the most challenging of these. because in the other cases you get only silver ammonia complex ion. The difference is that when you treat silver oxide with ammonia, now you get hydroxide ion as a product, as well as the silver ammonia complex ion. But when I treat silver oxide with this system, now I got ammonium ion in there, so I'm not making any hydroxide ion as product. That should be more than enough information for you to complete these equation writing tasks, and then proceed with the equilibrium analyses which these questions ask you to tackle. You tackle them. If you have difficulty, you got ample time between now and the next exam to come and ask us about it. We've told you the chemistry, or at least how to get at the chemistry, and that's what counts. Now then, the last issue raised by considerations in Chapter 19 is that of chemistry students' favorite task, writing equations for reactions. Statement: there is no question that the most difficult task for you folks at this stage of the game is to write equations for reactions. This is the hardest part of this, because you're not familiar with this. And I'm jumping up and down, do everything I can to try to get you familiar with this stuff as quickly as I can. But, as we have said, the simplest, best, most direct way to say a whole lot about a chemical reaction is to write the correct equation for the reaction. That's why this equation writing business is so important. But we know for sure, in order to have any chance to write a correct equation for a reaction, what do we have to do first?
Inventory.
Bingo! If you don't inventory and pay attention to what you got, you have no chance. That's how we attack this gas business. So, for question 1932, let me give you some parts of these puzzles. And you finish the task by writing the equations. Part A. I am considering a water solution containing cuprate ion. If cuprate ion is present, look at the formula for this stuff. If cuprate ion is present in water solution, do you think the solution is acidic, basic, or neutral? You think it's quite basic? Sure, you've got to have an abundance of hydroxide ions to make that stuff. Now I want to try to get you in the habit of letting these formulas talk to you. So if I take a water solution containing this and treat with H2S, hydrogen sulfide, you think some acid-base chemistry will take place? And along with this, we are telling you, this is a given in the statement of the question, that copper sulfide is damn stable. So you shouldn't be surprised to realize that treating this with H2S makes copper sulfide as the copper-containing stuff. You finish the equation. Second case, B. We've been through this before. Calcium hydroxide, solid, is treated with ammonium bicarbonate solution. Calcium hydroxide, composed of calcium ions and hydroxide ions. Do we certainly have the prospect of an acid-base reaction taking place? And then we know ammonium ion and bicarb ion are each stronger acids than water. Do you think ammonium ion might be part of this acid attack? Since ammonium ion is a stronger acid than bicarb ion? And since bicarb ion is a source of carbonate ion, do you think we might wind up converting calcium hydroxide to calcium carbonate? Given that calcium carbonate is a lot more stable, a lot less soluble in water than calcium hydroxide? You betcha. So you think bicarb ion is part of this chemistry? Well, I don't know how else I'm going to make calcium carbonate if bicarb isn't part of the chemistry. Do you also realize that for bicarb ion to be a source of carbonate ion, bicarb ion also has to behave as a Bronsted
Lordy acid.
Because you got to get rid of H plus from bicarb ion. All right? Part C. Calcium carbonate and calcium ion are part of this equilibrium system, which we have already analyzed on a number of occasions. Calcium carbonate saturated in water. We're going to take this equilibrium, calcium carbonate saturated in water, and hit it with ammonium sulfate solution. Well, what do we know? We know ammonium ion is a better acid than water. And we certainly know that there are components of this system, like carbonate ion, with which ammonium ion can react. We also know that sulfate ion is a potential precipitator of calcium ion. So I shouldn't be surprised to find out that calcium carbonate, at least in some amount, will be converted to calcium sulfate. D and E we just did. Over here. F. We've laid foundation for discussing F. Imagine we have a system where silver oxide, by treatment with ammonia, is in equilibrium with the silver ammonia complex ion. And silver ion. Take another look at F. Well, we were talking really here. F is to imagine taking the system for which we just wrote the equation, silver oxide treated with ammonium nitrate solution, where we got silver ammonia complex ion, silver ion, and if all the silver oxide was not dissolved, then also some silver oxide. We just a couple of minutes ago looked at writing the equation for that reaction. This system right here. So imagine we have that system in equilibrium existing before us. We treat it with a source of sulfide ion, specifically H2S. And in this case, we are telling ourselves, hey, silver sulfide is damn stable. It's a heck of a lot more stable than silver oxide, heck of a lot more stable than silver chloride, heck of a lot more stable than silver ammonia complex ion. It's damn stable stuff. So you shouldn't be surprised to find out that every form of silver ion existing in the original equilibrium, be it silver oxide, silver ammonia complex ion, or silver ion, becomes silver sulfide. You finish that. Now then, challenge problems. 19.1. To two significant figures, calculate S for silver sulfide saturated in water. I can tell you this, when I rewrite the notes, that's not going to be a challenge problem. It's not anything that's difficult at all given what we have looked at during our chapter 18 and 19 conversations. And I've even told you there, KW must be considered. But I'll ask you this. If you're going to calculate the solubility of silver sulfide in water, you think it might be requisite upon you to write the equation for the reaction that's established when water is saturated with silver sulfide? Nothing fancy about that. Write it right now. Let's go. What do you expect to be the products of this reaction?
Silver oxide and H2S.
Silver oxide? Not a basic system. Hydroxide ion? What else?
Hydrogen sulfide ion?
Hydrogen sulfide ion? Because what we're doing is paying attention to the the products which result from treating sulfide ion with water. They're going to wind up with any sulfide ion AQ stuff. And silver ion. Question. By definition, what is K for this equilibrium? By definition, what is K for this equilibrium?
It's 1 over KSP of Ag2S.
I'm asking. KSP for silver sulfide, absolutely. Notice that. There are materials for which the KSP expression will not involve the component ions. It involves one of the component ions, silver ion. But you can't write KSP for silver sulfide as a multiple of silver ion molarity times sulfide ion molarity, because you ain't getting any sulfide ion molarity in water. Question? We'll finish with this question today. Go back to well, I can write it faster than this. We just talked about this before. We've analyzed this on a number of occasions. This system. Can I take this as a legitimate KSP expression for calcium carbonate? Can I take that as a legitimate KSP expression for calcium carbonate? Does this reaction not correspond to what happens when calcium carbonate is dissolved in water? Does this reaction correspond to what happens when calcium carbonate is dissolved in water? Look at the reactants. Calcium carbonate, water. Yes, that's also a viable form of KSP, calcium carbonate. How about that? Analogous to what we wrote for silver sulfide, isn't it? We'll pick it up from this point next time.